In this lecture today, we'll be now taking up the analysis of nonlinear systems. So far, we have discussed the properties of nonlinear systems. We have discussed some commonly occurring nonlinearities. Now we have to deal with the analysis using the mathematical model of the nonlinear systems that we'll be seeing. We have to perform the analysis of these systems. So for that, we actually have 4 different approaches that we'll be looking at. One is the linearization method. Secondly, we'll be looking at the phase plane analysis. We'll be looking at the Lyapunov analysis, Lyapunov theory. And fourthly, we'll be looking at the describing function method. So using these 4 different analysis strategies, we'll be trying to find out how we can check a nonlinear system for stability, how we can design a controller for a nonlinear system, and also how we can be able to mathematically obtain a model of a nonlinear system. So these are the 4 methods that we'll be using in this we'll be studying in this course. These are actually only 3 methods: the phase plane analysis, the Lyapunov theory, and the describing function method. Lyapunov theory itself has 2 approaches. One is the direct method. Lyapunov gave the direct method and the indirect method. So indirect method of that was actually proposed by Lyapunov was the linearization approximation of nonlinear systems. So this linearization can be actually considered as a part of the indirect method suggested by Lyapunov. But when we say here Lyapunov theory, we'll be only talking about direct method, and in direct method we'll be using the nonlinear function itself, analyzing the nonlinear function and not the linearized model. So apart from the first that actually uses a linear equations, we actually have a nonlinear equation. We linearize it and then perform the analysis like we do in case of linear systems. All the other methods work are exclusively meant for nonlinear systems, nonlinear equations. The phase plane analysis is a graphical method. So using the state space model of a second order nonlinear system, we'll be able to plot the phase portrait of any second order nonlinear system, and then be able to analyze it for stability, for different for finding out the points, the equilibrium points of the system, for defining we'll be actually defining various singular points for a nonlinear system. That will be looking in case of phase plane analysis. Describing function method, it is based upon the Nyquist criteria, and it's actually a ratio of the output and input quantity that we'll be seeing. And using that describing function, we can actually phase plane analysis is limited to second order nonlinear systems only, but describing function method will cover up our higher order nonlinear systems as well. And then we have the Lyapunov theory. So Lyapunov, as I said, Lyapunov proposed the direct method of nonlinear system analysis and the indirect method of nonlinear system analysis. The indirect method itself is the linearization method, and the direct method, it again consists of it's actually based upon finding out the energy function of a system, and using that energy function, or what is also known as a Lyapunov function, we'll be able to define stability for a nonlinear system. So we'll be covering up these 4 methods in our coming lectures, and today we'll start with the linearization method. So it's also the direct method that is suggested by the indirect method that was suggested by Liapna. So where do we see linearization being used? For those systems where actually but deviation from linearity is not actually that much, and the system is, you can say that the system behavior is nearly linear, we can apply linearization approximation to such systems. Say for example we have magnetic saturation. So there is a curve we see here where flux varies with respect to the field current, and there is a linear behavior, and after some time the flux saturates and it no longer changes. So this behavior is not that much, there is not much deviation from the linearity in this case, as well as in case of amplifiers. We see this kind of behavior, the saturation region, and linear approximation is actually can be applied to such systems. So it can be applied to such systems which exhibit linear behavior but with slight deviations. Fine. So there is a non-linearity, but that is, there is a hint of linearity as well in the system. So we can apply linearization to such systems, as well as we can we need to have, the system has to be soft non-linear system. It cannot be having a hard non-linearity. As we discussed, for hard non-linear systems we cannot apply the principle of linearization. So now as far as linearization goes, there are three methods that can be used. Linearization by small signal analysis. Secondly, we have piecewise linear approximation. And thirdly, we have the harmonic linearization. So as far as the piecewise linear approximation goes, what we do is that we divide our segment into small pieces of small pieces, and these small pieces can be represented by linear differential equations, which then can be analyzed using linear control theory that we have already studied, and the solution will be actually the summation of all those individual solutions. Fine. So with this method, we can actually be able to obtain somewhat an approximately equivalent solution of the nonlinear system, and it will almost represent the exact solution of a nonlinear system, and this uh, can be extended, and we will be seeing this in case of the phase plane analysis of nonlinear systems. The harmonic linearization, it is actually based upon the frequency response method, and it actually forms the basis for the describing function method. So uh, we'll again be looking at this harmonic linearization, how actually a frequency response that we have already studied in case of linear systems can be applied for approximate solutions of nonlinear systems. We'll be seeing this uh, in case of uh, describing function methods. Now the first one that here is the linearization by small signal analysis is the one that we'll be looking at. Now we'll be looking at the linearization by small signal analysis. So using linearization by small signal analysis, what it actually does is it uses the Taylor series expansion to and using the Taylor series expansion we'll be actually finding out a particular operating point, and around this operating point we see that we assume that the behavior of the system is linear in the neighborhood of this operating point, and around this operating point the Taylor series expansion will be used for approximating for obtaining the linear model of this non-linear system that will be in that will be having. So if, for example, we have a nonlinear dynamic equation given by y is equal to f of x. Now what we'll be doing is we'll be finding out the Taylor series expansion of the system, and the Taylor series expansion of the system will give us y equal to y will be equal to f of x naught plus df by dx at x equal to x naught plus d2f by dx square at x equal to x naught and multiplied by x minus x naught whole square divided by 2 factorial plus so on. Now y is equal to fx is a nonlinear equation. Using the Taylor series expansion we can obtain the solution of y will be equal to this. Now we know for this very case that what happens here is this actually multiplied by x minus x naught here. We'll be actually finding out the behavior of the system around the operating point. So x minus x naught is going to be very small. So x minus x naught square is going to be even smaller. So all these terms that will come after this will be very small. Therefore, this function will can be approximated to y is equal to f of x naught plus df by dx at x equal to x naught into x minus x naught. So this here will actually give us the linear approximation of the original equation y equal to f of x. So this is what we do using the linearization by small signal analysis. We have a nonlinear equation. Using the Taylor series expansion, we expand it and approximate it by equating all other terms, by equating these terms equal to 0. So this equation here represents a linear differential equation, linear ODE, and this can be then we can actually understand the behavior of this linear ordinary differential equation through the linear by the linear theory already that we have covered, and find out the stability of the system. Now we'll apply the same, we'll extend this method to the state space model that we have been using. So normally in case of linear systems, we take the state space model as x dot equal to ax plus bu. Fine. So these are actually functions of time. Instead of writing x dot equal to axt plus but, for nonlinear systems the state space equation is written as x dot equal to f of xt ut plus so this, since as we saw in the example, we cannot actually segregate x1 x2 and sign so it's not possible to do that. So we have a combined function that can be used to represent the state space model, x dot equal to f of xt comma u of t. So now what will be the steps that we'll be following to find out the linear model of this particular system? We'll be doing an example later. First thing, we'll be finding out the operating points of the system. Determine the operating points. Now the operating points, let that be x naught and u naught for this system. The operating point is actually refers to the equilibrium point of the system. So at equilibrium point we have already seen that x dot is equal to 0. That means at this point f of x naught t and u naught t will be equated to 0, and from that we can actually find out x naught and u naught of this system. Then let this be equation number 1. Now from the Taylor series expansion we saw that we put y is equal to f of x naught plus d by dt df by dx of df by dx at x equal to x naught into x minus x naught. Fine. So using that same approximation method, what we will do is we assume xt is equal to x naught plus delta xt and ut is equal to u naught plus delta ut. So we are actually trying to make this equation in line with the Taylor series expansion, the linearized model of Taylor series expansion. Fine. Now we have these two equations. Substituting them in this original equation, let this be 1, this be 2, this be 3. So from 1 and 3 what we'll be getting is d by dt of x naught, we actually x dot equal to f of xt ut. So this is x dot, but we have put x equal to x dot plus x naught plus delta xt. So this is x dot equal to, what will this be equal to? This will be simply be equal to x naught dot plus delta x dot of t. Fine. Which is equal to f of x naught. We can put this again back as a function xt u naught plus delta ut, which can be approximately be written equal to f of x naught u naught plus a delta xt plus b delta ut. So f of the linear, the x dot is equal to axt plus b plus but. Now we can apply that here because our system is linearized model, and we can use that function to find out a and b. Now comparing this with the Taylor series expansion, a will be equal to here delta f by delta x at x naught u naught. Fine. And b will be equal to delta f by delta u at x naught u naught. Fine. And if we expand this, a will be equal to delta f1 by delta x1, delta f1 by delta x2, so depending upon the number of states, delta f1 by delta xn, delta f2 by delta x1, so on up to delta fn by delta x1, delta fn by delta xn. This will be our A matrix, and our B matrix delta by delta u will be equal to delta f1 by delta u, delta f2 by delta u, so on up to delta fn by delta u at x naught u naught. And in this very equation that we have, we have to get rid of x naught u naught that we have already obtained using equation number 2, f of x naught u naught equal to 0. We have obtained those values. So putting those values or subtracting this from that equation, subtracting equation 2 from equation number 4, we'll be left with delta x dot t equal to a delta xt plus b delta ut. So this equation gives us the linearized model of the nonlinear equation that we have in place, and while as A and B matrices can be obtained using these formulas. So we'll take an example, and using an example we'll be able to see what we have done. We'll take the van der Waals oscillator. So we'll be using this example van der Waals oscillator in a number of situations, because van der Waals oscillator also displays the property of limit cycle. So we'll be studying this there also in phase-based analysis, finding out the linear limit cycles. So once we find out the equations of the system, we get these two we find that the state space model of the system is like this. x1 dot equal to x2 and x2 dot is equal to mu 1 minus x1 square x2 minus x1. Fine. And now we want to find out the linearized model of the system, and from that we can actually see whether our system is stable or not. So these two equations can be put in the state space model in the matrix form. X dot equal to x2 mu 1 minus x1 square x2 minus x1, which is equal to f1 of x f2 of x. So first of all we need to find out the operating point of the system, and for that we'll equate x dot equal to 0. So once we equate x dot equal to 0, what we'll be getting is x2 is equal to 0. Fine. And mu 1 minus x1 square x2 minus x1 is equal to 0. Mu 1 minus x1 square x2 minus x1 equal to 0. So since x2 is already 0, so that means x1 is also equal to 0. So for this, the operating point is 0, 0. Fine. Now we need to find out the A matrix and the B matrix of this system. A matrix will be given by delta f1 by delta x1, delta f1 by delta x2, delta f2 by delta x1, delta f2 by delta x2, so f1 is this, f2 is this. So f1 partially derivating x2 with respect to x1 gives us 0. Partially derivating x2 with respect to x2 will give us 1. Then differentiating this with respect to x1 and with respect to x2. If we differentiate this with respect to x1, we'll be getting mu x2 is common. This is actually mu x2 minus mu x2 x1 square. Mu x2 will already be 0. So this is minus 2 mu x2 x1. Minus 2 mu x1 x2. And differentiating this with respect to x2. So that gives us mu 1 minus x1 square. So this is our A matrix, but we have to, this is given at x naught. Fine, we have to find it out at x naught. So x naught is already equal to 0, 0. So when we substitute x1, so when we found out the derivation of this was minus 2x1 x2 minus 1. Fine. So for that we need to put now x1 and x2 equal to 0 to get rid of this. So this is 0, 1. Put x1 x2 equal to 0. This becomes 0. This remains only minus 1 here. X1 equal to 0. This remains mu here. So this is our A matrix. For this particular case, our example, we have plus 0u plus 0u. So there's actually no differentiation. We do not need to find out B matrix in this case. So this is our A matrix. Therefore, simply putting, our linearized model of the system will be x dot equal to ax, or in other words, we can say 0, 1, minus 1 mu times x. So this is our equation. If we want to find out whether this system is stable or not, we know we have to find out the eigenvalues of this system, and the eigenvalues of this system, lambda 1 minus lambda 1 minus a, so that is lambda 1 minus 0, 1 plus 1, lambda minus 0, lambda I minus a, lambda minus 1 plus 1, lambda minus mu equal to 0, which implies lambda into lambda minus mu plus 1 is equal to 0, which gives us lambda square minus mu lambda plus 1 equal to 0, which gives us lambda 1 lambda 2 will be equal to minus b plus minus under root of b square minus 4ac divided by 2. So we have mu by 2 plus minus under root of mu square by 4 minus 1 is are the roots of the system. So now they are depending upon actually the value of mu. So if the mu is greater than 0, so if you put mu greater than 0 here, lambda 1 lambda 2 will be lambda 1 lambda 2 may have positive values, so this system will remain unstable. Fine. So if mu is equal to 0, if mu is negative, so accordingly it will vary. So mu is actually positive, and for this system it represents an unstable system. So linearized model of the Van der Waals oscillator that we have found is a unstable system. So this is our system here, x1 dot x2 dot, a nonlinear system. Fine. And what we did is first of all equated these two equations to 0, x1 dot equal to 0, x2 dot equal to 0, find out the values of x1 and x2. This will be the operating point, and differentiate this x1 dot and x2 dot individually with respect partial derivation with respect to x1 and x2, x1 and x2. Find out the 4 elements of A matrix. Similarly, if there was any dependence on U, you would have found out B matrix. In this case, B matrix will simply come out to be 0, even if we differentiated df1 by du, df2 by du, since none of the equations have U term in there. So df by du, df2 by delta u will simply come out to be equal to 0, 0. So this will be the B matrix in this case. So you can say x dot equal to ax plus bu. For this particular case, it will be 0, 0 times u. So this is the A matrix. Then after substituting the values of x1 and x2 that are obtained at the operating point, substitute it here as well as here, the operating points. Find out, this is your linearized state space model now of the system. Once you have the linearized state space model, then you can find out whether the system is controllable, whether the system is observable, what are the states, whether the system is stable or not. So all that analysis you can do in the linear domain once you have the linearized model. So this is one example. You can take another example and try to find out whether the system is stable or not using the linearization approximation. Do it for the simple pendulum case that we had obtained last time. X1 dot equal to x2 and x2 dot minus g by L sine theta. So for these two cases, again you have to equate them to 0, find out x1 and x2, then differentiate them with respect to x1 with respect to x2. The sine theta is actually sine x1. Then substitute the values of x1 and x2 that were obtained at the operating point in that linearized model. Find out x dot equal to x plus bu. Again, there is no dependence on u in these two examples. If you have torque here, then only if we are saying there is some torque we are applying, in that case we can say this is minus I guess minus ml square something. So you can check that what we had obtained, tau by ml square. Either you can say that torque was equal to 0, and then in that case input u is 0, or you can say we have tapped some amount of torque, so accordingly we'll have to take this value 1 by ml square times tau as well. So you can do this example, find out the equilibrium points, x1 dot equal to 0, x2 dot equal to 0, find out x1 and x2, then differentiate them with respect to x1, differentiate them with respect to x2, find out the A matrix, then differentiate with respect to u, find out the B matrix. Then you can put the operating points in those matrices and obtain A and B matrix. Then you can find out whether this system is controllable, whether this system is observable, or whether this system is stable or not. So that's all for this session. We'll continue in the next session.